Today, Australia is an island continent. If you travel to the state of Victoria and stand on the edge, you will see the Southern Ocean. And somewhere, thousands of kilometres away, lies the frozen continent of Antarctica. But it turns out, Australia wasn't always on its own. If we backtrack to 145 million years ago, we would see that Australia and Antarctica were once joined, and animals could walk between the two continents unimpeded by ocean, something that could not be accomplished today. From 145 to 90 million years ago, the only evidence of this eventual separation was a great valley between the two landmasses. Hi everyone, Andrew here. In this episode of Prehistoric Australia, we're going to be talking about the Lost Valley between Australia and Antarctica. The Lost Valley between Australia and Antarctica actually has a proper name. It's called the Antarctic Australian Rift Valley. Now, in order to understand this area, we first need to know where it came from. Our present understanding of the Rift Valley's history comes from geologists studying volcanic and sedimentary rocks in southern Victoria. By examining these rocks, they can tell us the story of Australia's ancient past. The Gippsland and Otway basins in southern Victoria are filled with ancient rocks. Scientists can then date these rocks using microscopic fossils of plant and animal structures. So, which formation has rocks that date back to the early Cretaceous period and can be found in the Otway and Gippsland basins? The Eumeralla Formation. The Eumeralla Formation, also informally known as the Wonthaggi Formation, dates back between 125 and 100 million years ago. Paleomagnetic studies of these rocks, coupled with those from Antarctica of the same age, tell us a lot about where and when the tectonic plates were drifting apart. So what was the origin story of the Antarctic Australian Rift Valley? Well, to find out that, you need to go back to the Jurassic period, back in time to when Australia was a small cog in the machine known as Gondwana. The supercontinent of Gondwana dominated the southern hemisphere. Australia was positioned in the southeastern corner, right at the bottom of Gondwana. Tectonic activity between Australia and Antarctica only began 152 million years ago, right at the end of the Jurassic period, as evidenced by the volcanic rocks found in the Gippsland Basin of Victoria. As a result of this later tectonic activity, Antarctica and Australia remain mostly attached throughout the Cretaceous period. A little known fact, however, is that Australia and Tasmania also tried to separate as well. A brief period of rifting occurred in the Bass Basin during the early Cretaceous. As a result, the Antarctic Australian Rift Valley stretched above Tasmania and below it. However, it was a failed rifting event, as we know today. You can't escape the mainland that easily, Tasmania. By 120 million years ago, Australia and Antarctica had peeled apart a short way across the Great Australian Bight, all thanks to the new oceanic crust which was thrusting its way in between their continental crusts. This new ocean crust temporarily represented low-lying land between the two continents. We would have seen a low, wide valley between two continental slopes. This tectonic formation is known in geology as a graben, or a rift valley. So there you go, that's how the Antarctic Australian Rift Valley formed. But what about the local climate? The local climate was particularly interesting. It was both warmer than today, but also regionally colder. Let me explain. On the one hand, the Rift Valley was within the Antarctic Circle, but not covered in glaciers. This was because Earth during the Cretaceous period was a hothouse world. The global average was 10 to 17 degrees hotter than today. Higher global temperatures were likely due to high levels of carbon dioxide in the atmosphere, reaching peaks of 2030 parts per million. In contrast, the highest carbon dioxide levels on record today were in 2019, reaching only 409 parts per million. So you can imagine how hot the world was back then. There were no permanent ice caps at the South Pole. Despite this, there is evidence that the Cretaceous environments of Antarctica and Australia did experience temporary frost. Scientists have calculated that temperatures reached as low as -8 degrees Celsius in the winter months, which is actually pretty balmy compared to Antarctica today. Periodically, however, temperatures may have dropped even low enough for glaciers to be present. This possibility is suggested by dramatic drops in carbon dioxide levels during the early Cretaceous to below 400 parts per million, which is very close to today's carbon dioxide levels. Mineral structures known as glendonites have also been found in South Australia and date back to the early Cretaceous. Glendonites form when soils are exposed to seasonal freezing and thawing, but only in temperatures below 4 degrees Celsius. This suggests that the climate may at times have been quite cold, with winter ice and seasonally frozen ground. Overall though, the mean average temperature in Victoria during the early Cretaceous was between -2 and 3 degrees Celsius. So yes, the combined evidence says that despite the Cretaceous world being much hotter than the world today, the local climate around the Antarctic Australian Rift Valley would have experienced temporary periods of ice and snow, and maybe even periods of minor glaciation. So overall, the climate around the Antarctic Australian Rift Valley was cold, wet, and seasonal. And it's all thanks to Australia being positioned at the bottom of the world at this time. Paleomagnetic studies of volcanic rocks indicate that southern Victoria would have been positioned between the latitudes of 70 and 85 degrees south during the early Cretaceous period. Being within the Antarctic Circle meant that southern Victoria would have experienced seasons much like those from polar regions today. Summer experienced 3 or more months of 24-hour sunlight. Meanwhile, autumn and spring had fluctuating lengths of daylight and darkness as they approached and departed the summer and winter months. Finally, the winter months would have been the greatest challenge to life in the polar forests. 3 or more months of 24-hour pitch black darkness, with only the moonlight illuminating the Rift Valley once a fortnight. And of course the southern lights, the aurora australis, making cameo appearances, dancing and waving across the black sky. I enjoy mountain climbing. It's a bit of a hobby of mine. And I always like to imagine what it'd be like to trek to the top of the Antarctic Australian Rift Valley and then look down on the valley below. And I imagine that what you'd see are 3 distinct paleo environments from that vantage point. And it'd be such a sight to behold. The first and most obvious paleo environment would be the forests, because they'd be all around you. And from that vantage point at the top of the valley, it would be so easy to see how far those forests extend. Forests once covered the slopes of the Antarctic Australian Rift Valley. The canopy consisted of ginkgo trees, tree ferns, podocarps, and other conifers. The understory, meanwhile, contained ferns, fungi, and horsetails. We know all this because fossils of these plants have been found in the Umaralla Formation. Trees in these polar forests grew widely spaced apart from other trees. That way, both the understory and the canopy would receive as much sunlight as possible during the summer months. Botanical newcomers to the polar forest included angiosperms, commonly known as flowering plants. Microscopic pollen from angiosperms have been found in the Otway Ranges of southern Victoria, dating back to 126 million years ago. These flowering plants look similar to today's magnolias, buttercups, and laurels. But we've talked enough about plant life. What about the animal life living in these environments? Well, one of the most abundant groups of animals living in the Antarctic Australian Rift Valley environment were mammals. In fact, over 50 specimens of mammals have been found in the Otway and Gippsland basins. These fossils are dated to between 129 and 100 million years ago. All of the mammal fossils discovered bar one have been tiny lower jaw bones with teeth attached. The size of the jaws indicates that most of these mammals were very small, often fitting into the palm of your hand. Their teeth, shape and size varied, as they often do with mammals, but most were insectivores nonetheless. So many of these mammals would have been scampering about in the leaf litter in search of the insects they preyed upon, but they weren't alone. Living alongside these mammals were the dinosaurs. But what types of dinosaurs lived in these polar forests? What is definitely certain is that the most numerous dinosaurs living in these polar forests were small herbivorous dinosaurs. One of these knee ornithischians was called Leolanosaura amicrographica. Its teeth indicate that it fed on plants in the understory of the forest. Growth rings in its bones indicate that it was active all year round and did not hibernate through the dark winters. Fossilized burrows known as bioturbations have also been found, possibly suggesting that Leolennosaura and other Neornithischians may have spent time in burrows. Another Neornithischian which may have engaged in this behaviour was Diluvocurci picaringi. Fossil evidence for this dinosaur includes a tail, foot and vertebra. The foot of Diluvocurci shows signs of having been injured and healed well before it died, and this happened in another 4 specimens of Neornithischians. This suggests that these animals were living fast, dangerous lives. Perhaps they had to be wary of predators. Diluvocurci may have had to journey away from the forest and down to the river to quench its thirst. It was an open target in the floodplain paleoenvironment. The second paleoenvironment of note were the floodplains. Now these were wide, low-lying areas of land that were situated at the bottom of valleys, and they contained a labyrinth of cold rivers and streams. We know this because of the sandstone, mudstone and siltstone deposits found in the Gippsland Basin of southern Victoria today. These were formed when sand, silt and mud were washed downstream from volcanoes. They were carried westward and eventually settled as layers on the bottom of rivers and lakes in the Antarctic Australian Rift Valley system. Over millions of years, these layers were compressed into rock. These could only have formed if braided river systems were present. During spring, there is evidence of seasonal flooding that may have occurred in the Rift Valley system. Now, how do we know this? We know this because of fossil soils known as paleosols that have been found in Alexander Island in Antarctica. These soils indicate that the ancient Antarctic forests were seasonally dry during the winter periods. But sandstone and mudstone deposits in the same area also indicate that sand and mud in rivers became layered under conditions of highly varying energy. The Victorian rock layers tell the same story. A possible explanation is that the winter ice and snow melted from higher ground during the springtime. The meltwater rushed down from the eastern volcanoes and from the slopes of the Rift Valley and flooded the rivers below, bringing large amounts of sediment with them. These layers of sediment are how we know that the Australian Antarctic Rift Valley experienced seasonal flooding during the springtime. Enduring this seasonal flooding were the plants living on the floodplains. They included lycopods and mosses. Meanwhile, the nutrient-rich rivers were abundant with isotales and liverworts. In the skies above, pterosaurs took to the wing. Probably 2 species could be described from the fragmentary fossil remains of Dinosaur Cove, but has not been so far. Sharing the skies were birds. The fossilized wishbone from an Enantiornithus specimen proves their presence in this environment. Dinosaurs such as birds and non-avian theropods occasionally walked across the floodplains, perhaps for a drink at the river. We know this because their footprints have been fossilized as tracks and discovered millions of years later. On ground level, if you were to gaze into one of the fast-flowing rivers that crisscross the plains, you might catch a glimpse of the giant amphibian Coolosuchus clearlandi. It was the last temnospondyl ever, reaching lengths of up to 3 meters long. It fed mainly on fish and spent most of its time submerged beneath the water. But even Coolosuchus may have had to watch its tail, for it shared these waterways with other large predators. Fragmentary teeth and bones found at Dinosaur Cove and other Victorian sites match that of small-bodied plesiosaurs and even a large 4 to 5 meter pliosaur. These animals may have found more room in freshwater lakes, and luckily for them, there were plenty around. The third and final type of paleoenvironment that existed within the Rift Valley system were freshwater lakes. Between 118 and 115 million years ago, the most famous lake in this area was the Koonwarra Lake. It was a small lake situated near a much larger lake. Most of the time these 2 lakes were separated by a narrow band of land, but occasionally the banks of the lake would break. This mass influx of water dropped oxygen levels to lethal levels, causing the fish in the pond to suffocate en masse. This tragic event will be fossilized in exquisite detail and is known to scientists as the Koonwarra fossil bed. Above the lake's surface, insects were abundant. Some insects took to the air, some were amphibious, while others crawled through the terrestrial vegetation. Fossil insects that have been found at Kumwara include beetles, flies, mayflies, damselflies, cockroaches, stoneflies, weta, booklice, scorpionflies, caddisflies, and wasps. You know what? If we keep talking about insects, this video is going to be 2 hours long. Instead, my pick for most interesting insect goes to Tarwinia australis. It was essentially a stem flea, or a proto-flea, or a flea before the true fleas. This species was physically similar to those fleas today found on bats, leading some paleontologists to suggest that its main hosts were in fact pterosaurs, although they do admit that its traits weren't specialised enough for one type of animal, so these proto-fleas most likely changed hosts a lot. The lake itself was probably quite brackish, as evidenced by the presence of fossilised algae. Beneath the surface, however, was a thriving community. Bottom of the food chain were the plankton. These included crustaceans such as water fleas and seed shrimps, as well as juvenile flies. Feeding on the plankton were the bottom feeders. Living on the lake bed were the juvenile forms of many types of insects, including mayflies, damselflies, stoneflies, scorpionflies, and beetles. Other bottom dwellers included fairy shrimp, crayfish, bryozoans, and freshwater bivalves. My favourite bottom-dwelling resident of the Kumwara Lake was a type of freshwater horseshoe crab called Victorlimulus mcqueenii. Why is this important? Well, I just think it's really cool because you don't often see horseshoe crabs in a freshwater setting. They're normally marine animals. So it's really cool to know that they did once live in this type of setting. All these creatures made the freshwater lake their home. In fact, many animals and plants thrived in the polar forests, floodplains, rivers and lakes. This dynamic combination of paleo environments made the Antarctic Australian Rift Valley a polar paradise for the organisms living there. But today, they're all gone. Why? How did this valley become lost to time? Well, the death of all continental relationships, plate tectonics. Geologically speaking, the Antarctic Australian Rift Valley was a long-term relationship. In fact, it was a relationship which lasted from the late Jurassic period to the late Paleogene period. Rocks in the Eumerella Formation show that active rifting between Australia and Antarctica had majorly slowed down by 100 million years ago. Rifting continued at this slow pace throughout the late Cretaceous period. This was only punctuated around 94 million years ago by rifting off the southern coast of Western Australia. In fact, this rifting was so major that by 83 million years ago, the once existing land connection between Antarctica and Australia was completely separated from Western Australia up to the border of Victoria. However, the rift valleys around Tasmania, Antarctica and Victoria remained high and dry. It was not until after the extinction of the non-avian dinosaurs, well into the age of mammals, did Tasmania finally let go of Antarctica. During the Eocene epoch, 46 million years ago, rifting rapidly accelerated. Marine deposits show that the Rift Valley became wider and wider until eventually seawater completely engulfed the widening valleys. By 30 million years ago, during the Oligocene epoch, Australia and Antarctica had been completely torn apart, meaning that the Antarctic Australian Rift Valley was lost to time forever. I've stood on the south coast of Australia and looked out upon the Southern Ocean, and even I find it difficult to imagine a landscape other than ocean in its place. But make no mistake, there was once a spectacular valley. A valley where the forests saw winter darkness for months on end. A valley where dinosaurs walked across the floodplains. A valley where the freshwater lakes were a breeding ground for horseshoe crabs and the rivers were a haven for the last giant amphibians. Life in these polar valleys was a remarkable achievement for plants and animals alike. But now we can only look back and imagine what it must have been like to behold the lost valley between Antarctica and Australia. Thanks for watching, guys. Hope you enjoyed that video. I gotta tell you, it was really intensive to research, so I hope you learned a little bit. In fact, comment below What did you learn from this episode that you didn't know before about Australian prehistory? I would love to know, so please leave it in the comments below. Also, make sure to like and subscribe to the channel, and feel free to support us on Patreon. Any support at all really helps to keep the channel going. So thanks guys, we'll see you next time.